Hey everyone! In this video, we're going to talk about some concentration units, which is related to our first goal of the course, to use concentration units to solve problems about aqueous solutions. These are some commonly used concentration units, and I probably don't even have to remind you that molarity is abbreviated as a capital M, and it stands for moles of solute for every liter of solution. We'll be working with molarity a lot this semester. Molality is abbreviated lowercase m, and molality you probably haven't seen in a while. You talked about molality in Chem 2 when you learned about colligative properties like boiling point elevation and freezing point depression. Molality, just to remind you, stands for moles of solute for every kilogram of solvent. But we won't be doing many problems involving molality this semester. There will be plenty with molarity, plenty using parts per million and parts per billion, and plenty using weight percent. In this video, I wanted to focus on parts per million, and in other videos, we'll focus on weight percent. First of all, parts per million and parts per billion are used for very small concentrations. In fact, the EPA uses these units a lot for the maximum contaminant levels of certain solutes in solution. If I remember correctly, the maximum contaminant level for lead is 15 parts per billion. Now, just to give you an idea of how small a part per million is, can you imagine traveling from Boone to Blowing Rock and back? That round trip is roughly 16 miles, and 1 part per million of that round trip would be an inch. So 1 inch out of 16 miles, that's a part per million. So I hope you appreciate how small that unit is. Let's define them a little bit more clearly. So when we're talking about aqueous solutions, it's helpful to think of a ppm, a part per million, as 1 milligram of solute for every liter of solution. And a part per billion would be 3 orders of magnitude smaller. So instead of having milligrams of solute upstairs, you would have microgram. 1 microgram of solute for every liter of solution. Those are some handy definitions of ppm and ppb to keep in mind. Now, another way to express a ppm, if you look at this numerator and denominator and divide both by 1,000, that would give you microliters of solute upstairs and milliliters of solution downstairs. So if you ever see a unit that's micrograms per milliliter, that's also a ppm. And if you really wanted to go crazy, you could divide again upstairs and downstairs by 1,000, and you would have nanograms of solute for every microliter of solution. So if you ever see this unit, that's the same thing as a ppm. I find that the most convenient way to think of ppm and ppb is milligrams per liter, or for ppb, micrograms per liter. Now, that's when we're talking about aqueous solutions. What if we're talking about solids? And this may be more useful for when you're actually working in the lab. But a ppm If we've got some solid sample, like a soil sample or a sediment sample, would be 1 milligram of solute for every kilogram of solid sample. Again, whether that's soil, sediment, or whatever. And again, if you were to divide upstairs and downstairs by 1,000, that would give micrograms per gram, still a ppm. And then a part per billion, well, if you look at our definition of a ppm, a part per billion is going to be 1,000 times smaller. So that would be 1 microgram of solute for every kilogram of solid. You may need a little bit of time to process these definitions, but let's try to do a problem. So here they're telling us that we have 12.6 ppm of a calcium nitrate solution, and they want to know the concentration of nitrate in parts per million. So in other words, they're saying you have 12.6 ppm of calcium nitrate, and they want to know how many ppm. And if I want to, maybe I'll remind myself that ppm is milligrams of nitrate for every liter of solution. This is what we're being asked to find. I'm going to begin with what we're given, and I'm going to rewrite the definition of ppm as milligrams per liter. So we've got 12.6 milligrams of calcium nitrate for every liter of solution. That's our starting point. And one thing I'm liking so far is that my denominator is already where it needs to be. I've got liters of solution downstairs, and that's how I want to end up. The only thing we need to worry about is converting milligrams of calcium nitrate into milligrams of nitrate. Let's try it. Before we begin, it may be helpful to remember that for every 1 mole of calcium nitrate, how many moles of nitrate do I have? Well, look at your subscript. For every 1 mole of calcium nitrate, you've got 2 moles of nitrate. So if it helps you to actually see that equation written out, go for it. 100% of that calcium nitrate dissociates into 1 calcium and 2 nitrates. So writing this equation has helped me remember that for every 1 mole of calcium nitrate, we've got 2 moles of nitrate. So I'm thinking we're going to have to convert these milligrams of calcium nitrate into moles. So I'm going to say 1,000 milligrams of calcium nitrate are in 1 gram. And then I'm going to use the molar mass of calcium nitrate to convert into moles. So for every 1 mole of calcium nitrate, I'm going to have 164.09 grams of calcium nitrate. And then now I can either use this equation I've written, or I can just look at the formula and remind myself that for every 1 mole of calcium nitrate, I've got 2 moles of nitrate. And then from there, it shouldn't be too hard to get milligrams of nitrate. For every 1 mole of nitrate, there are 62.005 grams of nitrate. And then finally, converting grams into milligrams is the final step. So again, we have milligrams of nitrate upstairs, liters of solution downstairs. These 1000s cancel. And when I did the arithmetic, I got 9.52 milligrams per liter of nitrate. Or if I wanted to, I could just say 9.52 ppm of nitrate. Either answer would be acceptable, and I think I followed the rules for sig figs correctly too in this problem. Let's try another one. So now they're telling us that we've got a rainwater sample and that it's 0.2 ppb of this alkane. So I'm going to rewrite ppb as micrograms of that alkane for every liter of solution, and our solution is rainwater, but I'll just call it solution. So they want to know what is the molar concentration. So molarity is moles of alkane for every liter of solution. And much like the previous problem, it seems like I don't have to do any work to convert the denominator. All the work is upstairs. And I think we can handle this. We've got 0.2 micrograms of the alkane for every liter of solution. And I need to convert this mass into moles. So first I'm going to get rid of micrograms, and maybe I'll convert that into grams. 1 gram of the alkane contains 10 to the 6 micrograms of that alkane. And now I can use the molar mass that they gave us. It looks like 282.56 grams of the alkane is in 1 mole. And I think that's it, right? We've got moles upstairs, liters downstairs, done and done. And did you see what I did here? I, for some reason, inserted an extra 0 there. It looks like my answer is only going to need 1 sig fig. When I did the arithmetic, I got 7.1 times 10 to the negative 10th molar. I told you ppb was for very low concentrations, so now I hope you believe me. That's it for this video. Thanks for listening and good luck.